Last time, we built up the concept of what a vector really is, an essential physical quantity that helps encode reality. Continuing from where we left off, we'll focus on some other properties of vectors which serve as foundational tools that you'll see again and again throughout physics. So let's dive in. Let's begin with a quick recap of what we already know. In a standard coordinate plane, we can describe any vector in terms of its components along two perpendicular directions, typically the x and y axis. These directions are captured by unit vectors I hat pointing right and j hat pointing upward. Together they form the basis of the 2D vector space, meaning any vector in the plane can be constructed as a combination of just these two. In physics, we mostly work with orthogonal bases like this, where the axes are at right angles and do not interfere with each other. Let's take an example. So here's a vector A, its magnitude is the square root of 13, and say it makes an angle of tan inverse 2/3 from the x-axis. So we can resolve this into its x and y components, ax and ay respectively. We would see that a goes 3 units along x and 2 units upwards along y. So these projections give us ax equals 3 hat and ay equals 2j hat. So the original vector can be written as a equals ax I hat plus ay j hat, or more concretely 3 hat plus 2j hat. This process of breaking a vector into components is called resolution, and it's going to be the key idea in everything that follows. Now, deciding on the coordinate axis for resolving vectors is not always straightforward. Consider a simple pendulum. As it swings, its position traces a circular arc, not a straight line. This means that at any instant, its motion isn't aligned with the usual x and y axis. If we pause the pendulum at this instant, where the string makes an angle theta with the vertical, and look at the different forces acting on it, we see the gravitational force acting straight down, as always, and we see the tension acting along the string. Now, take a ball rolling on an inclined plane with the angle of incline given as alpha. Once again, gravity pulls downward, but the surface is slanted and the ball rolls along the slope. So, how do we decide how to place the coordinate system in each case and thus choose directions along which we resolve the forces which make real physical sense? In both cases, while the gravitational force acts downwards, the motion, as we saw, occurs along a different direction. So, to analyze the forces acting on it, we need a rotated coordinate system that aligns with the direction of motion, which in case of the pendulum is at a tangent to the centripetal acceleration and tension, and in case of the ball on the incline, it is along the downward direction of the slope and thus tangent to the normal force. Thus, let's take a look at the vector decompositions for each case. For the pendulum, we align the coordinate axis such that the positive y-axis is along the tension and the tangential velocity is along the negative y-axis. We work in a similar fashion on the inclined plane, choosing our x-coordinate along the upward direction of the slope and the y-coordinate along the normal. Now, in both cases, we only need to resolve the gravitational force into its respective components. In case of the pendulum, one of the components lies along the string, which gives us minus mg cos theta j hat, and another perpendicular giving us minus mg sin theta I hat. At any instant, these components decide whether the tension increases or if the pendulum speeds up. As for the incline, resolving the gravitational force gives us mg cos alpha along the negative y direction, which balances the normal, and minus mg sine alpha, which acts against the frictional force in the negative y direction, thus causing the ball to roll downwards, given it exceeds the frictional force. So, whenever you're analyzing a system in motion, don't rush to work everything out in the generalized Cartesian system. First, figure out where the object in question is constrained to move, and thus the directions that reflect actual physical interaction, and use that to define your axis, which may be rotated or shifted accordingly. This would not only make vector resolution far easier, but also more intuitive to actually understand how it plays into the motion itself. Now that we have seen some actual examples, we can extend the principle of vector resolution to 3D. When a vector floats freely in space, how do we pin down its influence along familiar directions? Here's a vector v. As you can see, it has both magnitude and direction. Now, say we already have the measure of its magnitude given as absolute v, which I shall call simply v here, just to save time, but you should follow the actual notation as shown. Now, obtaining the direction will take some work, but I assure you, it's quite interesting and very simple once you understand it. So let's get on with resolving this vector onto the familiar planes and axes as we know, one step at a time. First, we draw the projections of the vector onto the y-axis and the xz plane. Now, if the polar angle, which is the angle between the vector and its xz projection, is theta, then we see a triangle formed enclosed by the vector, the vertical projection parallel to the y-axis, and the xz projection. Using basic trigonometry, we find the height of this projection, and the component along y is thus v sine theta. As for the projection on the y equals 0 or the xz plane, it would have a length of v cos theta. Now all we are left to do is further resolve this along x and z axis. That requires another angle, the azimuthal angle phi, as shown from the z-axis in this case towards the projection on the plane. Again, with some trigonometry, we get the x component as v cos theta sin phi and the z component as v cos theta cos phi. Thus, we have obtained all the components of the initial vector along the x, y and z coordinates, and assembling all of it together gives us v equals v cos theta sin phi I hat plus v sin theta j hat plus v cos theta cos phi k hat. You can try this out for a different set of right-handed coordinate systems, defining the radial and azimuthal angles differently, and obtain the results in a similar fashion. In the previous video, we saw how vector addition works. Now it's time to head on to vector multiplication, starting with the dot product, which is a powerful tool in vector analysis. To understand how the dot product works, of course, we need two vectors. Let's take vectors A and B, both starting from the origin, with B at an angle theta from A in the clockwise direction. Now, what the dot product of A and B does is measure how much of B lies along A and vice versa. To visualize that, we drop a perpendicular from the tip of B onto A, and that allows us to obtain B's projection or shadow along A, depicting how much of B points along A. We can see that this length is B cos theta, and A dot B is the product of this multiplied by the actual length of the vector A. So A dot B equals A times B cos theta. We can try to do this the other way round by projecting A onto B instead, and once again we obtain B times A cos theta, which is the exact result we previously obtained. Thus we see that A dot B is the same as B dot A, implying that the dot product is commutative and remains unchanged even if the vectors switch roles. In a different manner of understanding, we can also see that it does not matter if the angle theta we take from one vector to the other is in a clockwise or counterclockwise direction, it yields the same result. Also note that the dot product results in a scalar quantity, not a vector, as it gives us a measure of directional overlap. Hence, they are also called scalar products. Let's take a numerical example to master the concept of dot products when the vectors are expressed in terms of their x and y components. Say a equals 4i hat plus 2j hat and b equals 2i hat minus 1j hat. Algebraically, we multiply the same components together, so 4i of a with 2i hat of b and 2j hat of a with minus 1j hat of b. That gives us 4 times 2 plus 2 times minus 1, giving us 6. Very easy, as you can see. Now, once again we track back to the idea of the angle between the vectors and see how the dot product changes with that. When the vectors point in the same general direction, the dot product is positive. At right angles, that is, when the vectors are perpendicular to each other, the dot product becomes 0. And if you go beyond that, in opposite directions, the dot product becomes negative. Also, from what we have seen so far, we can arrive at a final formula to compute the angle between vectors, which can be written as theta equals cos inverse of a times b over the product of the absolute values of a and b. In physics, we shall see the dot product in many places, like in kinematics, when calculating the work done by a certain external force in displacing a box along an incline, or in electrostatics when computing the electric flux of a point charge through a surface. Okay, now time to explore the second type of vector product, the cross product. We begin with two vectors a and b placed on the same plane, and to form the cross product, we don't just look at their magnitudes or how aligned they are, we ask something else this time, that is, how much one vector spans across the other in a perpendicular sense. And we define the magnitude of the cross product as the product of the absolute values of a and b times sine theta, where theta is the angle between the two vectors. But this result isn't a number like in the dot product, it's a new vector. A vector that is perpendicular to the plane formed by a and b. You can see the highlighted parallelogram formed by the two vectors, and the area of this parallelogram is exactly the magnitude of the cross product. So geometrically, this product tells us how much area the two vectors sweep out together. Now let's think about direction. To define the direction of the cross product, we use the right-handed rule. Curl your fingers from the vector A to vector B. Your thumb points in the direction A cross B. In this case, notice how the fingers sweep counterclockwise from A to B. The resulting vector points out of the screen towards you. To represent this, we use a dot in a circle, and imagine this as looking straight at the tip of an arrow coming towards you. Now let's reverse the order from B to A. The fingers now curl the other way and the cross product points into the screen. That's shown with a cross inside a circle, like looking at the tail of an arrow disappearing away from you. So one thing you can see is that A cross B is equal to the negative of B cross A. This is a fundamental property that captures the handedness of space. Putting it all together, the cross product gives a vector of magnitude AB sine theta in the direction perpendicular to the plane of A and B, denoted by n hat. In this 2D setup, since both A and B lie in the xy plane, n hat points along the positive z axis. So in this specific case, A cross B is the magnitude times k hat. Throughout our physics journey, we shall see that the cross product is essential to describing rotational motion, torque, angular momentum, magnetic forces, etc. Literally anywhere, orientation in 3D space plays a role. Now, as we saw earlier, to understand the direction of the cross product, we use the right hand rule, and here's a short hand-drawn animation to make that easier for you to understand. Place your right hand so your fingers point along the vector A, then curl them towards the vector B through the smaller angle. Your thumb now points in the direction of A cross B, perpendicular to the plane formed by the two vectors. In this example, the thumb points outwards towards the viewer, so we represent the direction using a dot inside a circle. To fully understand how to compute cross product of vectors, let's switch to 3D. We begin with a 3D coordinate system, adding the x, y, and z axis. Next, we place the unit vectors I hat along the x-axis, j hat along the y-axis, and k hat along the z-axis. Now observe how cross products of these basis vectors behave. I hat cross j hat points along k hat, magnitude corresponding to the yellow parallelogram in the xy plane. J hat cross k hat gives I hat, seen with the teal parallelogram in the yz plane, and k hat cross I hat gives j hat, shown via the orange parallelogram in the zx plane. This cycle follows the right hand rule, curling from the first to the second gives the third vector. Now let's take two arbitrary vectors, vector A and vector B. We draw them in space, then form the parallelogram they span. Now the cross product of A and B, A cross B, is perpendicular to this parallelogram, and its magnitude gives the area of the parallelogram. Let's suppose vector A is given by the coordinates 2, 1, 1 and B by 1, 2, 0.5. So if we compute the magnitude of A cross B, we get 3.35, which is also equal to the magnitude of the resulting vector. So we can draw the resulting vector A cross B coming out of the plane as shown in red here, with the same magnitude as the area of this parallelogram. But how do we mathematically compute this vector product though? For that, we need to use a determinant formula. We write a determinant of a 3 cross 3 matrix, placing the x, y, and z components of vectors A and B in the second and third rows respectively, while in the top row we place the unit vectors I hat, j hat, and k hat. Now we simply expand this determinant as the sum of each term in the top row with its corresponding cofactors. So we get the following terms: 1 times 0.5 minus 1 times 2 I hat minus 2 into 0.5 minus 1 times 1 j hat and 2 into 2 minus 1 into 1 k hat. This finally simplifies to minus 1.5 I hat plus 3 k hat, which is our final cross product vector. This wraps up our exploration of vectors, how to represent and add them, resolve them, and combine them through dot and cross products. These ideas are central to the language of physics, helping us describe motion, force, and orientation in space. There's more to vectors, like scalar and vector triple products, but those are best studied later with the tools of linear algebra in a more mathematical setting. In the next video, we'll look at an elaborate problem which tests your understanding of vectors, ensuring you can handle even the toughest of questions you may encounter on JEE Advanced and breeze through them. After that, in a separate series of videos, we'll move on and focus on building the essential mathematical toolkit from trigonometry to calculus that we'll need before jumping into kinematics and classical mechanics. So if you enjoyed this video and found it helpful, do give it a like and don't forget to subscribe to Eigen Akademie, and I'll see you in the next video. Bye.